We're going to go over the questions for the multiple choice and free response that you had for the whole section on gravity. Looking at the first multiple choice question, it's asking if the distance between 2 point particles is doubled, then the gravitational force between them is which of the following. The general formula for gravitational force between 2 point objects is, or two spheres really, is F is equal to G m1 m2 over r squared. If you double the radius, some people's initial instincts is to assume that the force of gravity will also be doubled, or excuse me, decreased by a factor of 1/2 because r is in the denominator. But in reality, if you double the r and then you square that, you're really going to get 4r squared, which is going to reduce the force of gravity by a factor of 4, not a factor of 2. So your answer is A. For number 2, it says that the surface of the Earth, an object of mass m, has weight w. If this object is transported to a height above the surface that's twice the radius of the Earth, then at the new location, which of the following? For this one, you might want to draw it out because it could be easy. You can make easy mistakes. First of all, they tell you that you are at the surface of the Earth, and then you weigh w. And then you're going to move 2 times the radius of the Earth. That means your new radius isn't 2 times the radius of the Earth. You're going to move 2 times the radius of the Earth further away. So that means your total r is 3 times the radius of the Earth, where you were originally just at the radius of the Earth. So first of all, mass is constant, so you can also eliminate anything that says your mass would change, because your mass wouldn't change no matter how far away you are from the Earth. And then you have to look at what happens when you triple your r. What happens to your weight or your force of gravity? Well, looking at the force of gravity equation, if you triple the radius, and the radius is going to get squared, your new radius, then it's really 9r squared. So you're actually going to be 1/9 greater. Or remember, that 9 is associated with the denominator, so your force of gravity or weight is going to be 1/9 of what it was when you were on the surface of the Earth, meaning E is your best answer. For number 3, they give you a bunch of information that's kind of meant to doubt you. They tell you that a moon of mass m orbits around a planet that has mass of 100 m, and it says the strength of the gravitational force exerted by the planet on the moon is F1, and the strength of the gravitational force between the moon and the planet F2. Which of the following is true? Well, this is just basically a simple concept question. We have to realize that F1 and F2 are the same. The force of gravity of the moon pulling on the planet is equal to the force of gravity of the planet pulling on the moon. It's one of Newton's third laws. Gravity is an equal reaction force. If you weigh 800 newtons because of the planet pulling on you, you actually are pulling the planet with the same amount of force. It's equal but opposite, so your answer is simply C. For the next one, we have a situation. They're telling us that Pluto is 1/500th the mass of the Earth and 1/15th the radius of the Earth, and they want to know what the value of little g is of Pluto. So we have to find how the little g of Pluto relates to the little g of the Earth. Alright, so first we have to think about the force of gravity is equal to big G m m1 m2 over r squared. Let's assume big M is the mass of the planet and little m is your mass. If we also know that force of gravity is little m, your mass times your acceleration due to gravity, so which is equal to big G, the mass of the planet, times your mass over r squared. So we can cancel out, and basically little g is equal to big G m over r squared. Now, because the mass of Pluto is that's a little bit of a typo. The mass of Pluto is 1/500th the mass of the Earth, which to our little g equals big G m over r squared equation would affect it in a way that if something is 1/500th the mass of another object, its acceleration due to gravity is going to also be proportionally 1/500th. But we don't stop there, because even though it's much smaller than the Earth in terms of mass, it also has a smaller radius. The radius is 1/15th that of the Earth. And since the radius is in the denominator and it's being squared, the way it would affect the little g, the gravity, is if something has 1/15th the radius, then it would have 15 squared times the little g, which means it would have 225 times the acceleration due to gravity. So then our answer is, if we look at how the mass would make the gravity 1/500th and the small radius would make the gravity 225 times greater, and we said that the acceleration due to gravity of the Earth is 10. The reason we're going to use 10 is because we're rounding. We find that the acceleration due to gravity on Pluto would be 225 over 50th meters per second squared. Now, if you had like some people go to the natural reaction that they need to round everything, so then they end up with 9/2 meters per second squared, or about 4.5 meters per second squared, and then everything else is given to them in fractions. So if you were to do the rounding method, you would have to simplify everything, which will still give you the correct answer, but it'll be wasted time. So occasionally make sure what your options are. Something happened here, that was weird. There we go. So pay attention to what your options are set up as, because you might end up giving yourself much work, and then at the same time, remember, you're being timed. Let's go on to the next one. For this one, we have a satellite is currently orbiting the Earth in a circular orbit of radius r. Its kinetic energy is k1. If the satellite is moved and enters a new circular orbit of radius 2r, what will be its kinetic energy? For this one, we can deal with the fact that we understand that if something moves further and further away from the Earth, its actual velocity of stay in orbit decreases. It doesn't need to be going as fast because it's not finding as much gravity. So basically, if you move further away from the Earth, your speed is going to decrease. So your kinetic energy should be decreasing, which kind of narrows it down to A or B. To find out which one, we can go through the original equation. We know that when something is in orbit, its centripetal acceleration has to equal its acceleration due to gravity. If you haven't memorized the formula, you can still derive it. Centripetal acceleration is the tangent velocity squared over r, and acceleration due to gravity is big G m over r squared. The r's canceled out. We find out that the tangent velocity is proportional to the object's mass over the radius, which means if you double the radius of how far away you are, what you really did is you have to decrease the velocity squared by 1/2, which means the velocity decreases by a factor of square root of 2. If we look at what happens to the kinetic energy, if we assume the original kinetic energy was 1/2 mvt squared, and we decreased the velocity by 1 over square root of 2, which ended up being pointless because then when we clean it up, it becomes 1/2 m times 1/2 vt squared, which means the kinetic energy is going to be half the size of the original kinetic energy. So our answer ends up being B. The kinetic energy decrease is in half. This would be a different situation if we were talking about the momentum, since the momentum is just mass times velocity, not the same thing as energy, mass times velocity squared. The momentum actually decreases by a factor of 1/4, but the kinetic energy only decreases by a factor of 1/2. It's an easy way to ask you pretty much the same question, but give a different result. So I'll ask you, what will be the new momentum? Next question. For this one, we have a moon of Jupiter has a nearly circular orbital radius and an orbital period of t. Which of the following expressions gives the mass of Jupiter? So we have to find an equation that associates t, the period, and the mass. In terms of the period, if you're talking about velocity of an object around a circle, the velocity is equal to its distance, which is its circumference, times divided by its period, which is the amount of time it takes to complete one revolution. So velocity is circumference over period. And since centripetal acceleration is the velocity squared over r, we can say that the velocity squared is 2 squared, which is 4, pi squared, r squared over t squared. And if we divide all that by r, we can say that centripetal acceleration is 4 pi squared r over t squared. And like we said before, when something is in orbit, its centripetal acceleration and its acceleration due to gravity have to be equal for it to be in orbit. And then we have the equation 4 pi squared r over t squared is equal to big G m over r squared. So now we have an equation that it has both our period and mass in it. And we start going through our values to try to isolate the mass, and then we get 4 pi squared r cubed over big G period squared is equal to the mass, which matches E. So it's a lot of manipulating the equations. And if you don't have the equation memorized, hopefully you're able to derive it. Go on to the next one. So for this one, we have two large bodies. Body A has a mass of m, and body B has a mass of 4m, and they're located a certain distance away from each other. They want to know the point in which the gravitational force on an object will be equal to 0. So let's imagine that there is an object somewhere in between them. If the object is somewhere between them, basically the force of object A pulling on object M and the force of object B pulling on object M have to be equal to each other for something to experience no gravity. which means there, if we break it down, that means, and we assume that the distance from from object A and this unknown mass is x, we can set up the equation you have in front of you. So we can then clean up the equation, cross out all the stuff they have in common, and what we end up with is 1 over x squared. X is the distance from object A that this unknown object is. The mass of the unknown object doesn't really matter. Is equal to 4 over r minus x squared, which is the distance of the object to object B. We do some cross multiplication. We get r minus x squared equals 4x squared. We can square root both sides and get r minus x equals 2x. We solve for it, get r is equal to 3x, and then that means x is equal to r over 3. So the object would have to be 1/3 of the distance of objects A and B. It would have to be 1/3 of that from object A, which makes sense. It has to be much, much closer to object A to cancel out the gravity caused by object B. And that's the short mathematical way. You could also use some logic, but that would require like a little bit more of assumptions. Then we'll move on to number 8. Here they're telling us the distance from Saturn to the Sun is 9 times larger than the distance from Earth to the Sun, and it wants to know how long is a Saturn year. So you have to basically see how the proportions of a Saturn year compared to the proportions of an Earth year. So we have to try to find an equation that deals with period and radius to see if we can find a way to incorporate the years. So if we look at our basic equation that says velocity is equal to circumference over period, and we know the centripetal acceleration is v squared over r, and the centripetal acceleration is equal to the acceleration due to gravity, just like we did before. If we square the velocity, we know velocity squared is 4 pi squared r squared over t squared, and if we divide both sides by r, we have that the centripetal acceleration is 4 pi squared over r over 4 pi squared r over t squared, which is equal to little g, which is big G mass of the planet over r squared. In this case, the big M is the mass of the sun because it's the thing being orbited. We clean up the equation a bit, and we can isolate the period a little far. We can isolate the period, and we find out that that the 4 pi squared r cubed over gm is equal to the period squared. So if we look at the question, what the question is saying is, what happened to Saturn is 9 times the radius from the sun. Now, if you have 9 times the radius and you cube it, it's really like saying 720. You're going to increase your period squared by 729 times. So the period of the Earth squared times 729 will give us the period of Saturn squared. And then if we square root it, that means the period of Saturn is 27 times bigger than the period of the Earth. And if we say the period of the Earth is 1 year, then Saturn has a Saturn year is equal to 27 Earth years. And we have it here. Now, if you pay attention, you see that we have this 729 Earth years. If we had just broken down the equations, we would have thought that the Saturn takes 729 Earth years to go around. No, Saturn is 729 times the period of the squared period of Saturn is 729 times greater than the squared period of the Earth. But if we square root everything, we found out it's actually 27 years. And we plug it in, we actually get the correct value. This one's a little bit of a longer one. It says the moon has a mass of m and a radius of r. A small object is dropped from a distance of 3r from the moon's center. The object's impact speed when it strikes the surface of the moon is equal to k, big G, big M over r. And they want us to find the value of k. Alright, if we look at what we initially have, we're assuming it's being dropped from rest. We want to find the final velocity. The total drop, because it's being dropped from a radius of 3r, but it's obviously not going to go to the center of the moon, so it's only going to fall a distance of 2r. Now, initially we're tempted to use our kinematic equations since we already know 2 of them, if we can just find little g. But the problem is that the acceleration for our kinematics is equal to the absolute value of the acceleration to gravity, which is negative gm over r squared. So we want to just plug it in and then use that as our little g, but we're going to run into a problem because our acceleration is constantly changing. This is such a big drop that we can't rely on a constant acceleration due to gravity, and our kinematics equation only works if we have a constant acceleration, at least in the algebra term. But what we can rely on is, when we can't use kinematics, we can rely on our conservation of mechanical energy. We're going to assume there's no air resistance or anything to really remove energy from it. All that's happening is the potential energy is going into the kinetic energy. So the initial mechanical energy should equal the final mechanical energy. So the kinetic energy initial plus the potential energy initial should ideally equal the kinetic energy final plus the potential energy final. Kinetic energy is going to be 0 at the beginning. The potential energy initial, we clean that up and then we plug in our values. Now, remember, we have to use our potential energy due to gravity equation, which is, we talked about last class, is this crazy one that says negative big G m times the mass of the large object times mass of the other object divided by the radius, not the radius squared. Potential energy is just big G m1 m2 over r. And so we have the equation twice. 3r is the original radius from the height, and then r is because it's going to hit the ground, now go to the center. We clean it up a little bit, and we move the variables together, and we get the following: 1/2 mv final squared. We kind of keep simplifying. We get rid of the m's, and then we remove the g and the m since it's common variable. Now keep in mind it's big G m negative, because we're not moving the entire negative gm, we're just moving the big gm. So be careful that it's negative 1 over 3r plus 1 over r equals 1/2 v final squared. We clean it up again and we get the following equation: 2gm divided by 2 over 3r. We have to have common denominator. That's how we simplify that. Negative 1 over 3r plus 1 over r. We multiply the 1 over r by 3 on the top and 3 on the bottom, and that means that we get 4 over 3 times g big M over r is equal to v final squared. We square root that, and then we get our value for v final, and then we see that our k is equal to 4/3. Unfortunately, I'm gonna have to stop it here to keep this video under 20 minutes. In the next video, we'll go over number 10 and the free response.